All right, hey guys, here we go. This is Unit 1, Day 4 on the distance formula. So we use distance formula to find the distance, as the name would imply, between 2 points on the coordinate plane. So the formula that we're going to be using, which is a little bit tedious and can look a little bit overwhelming, but once you unpack it, it's not terrible. So this is going to give us the distance between 2 points, x1, comma y1, and x2, comma y2. So notice that these little numbers, 1, 1, 2, 2, those are just subscripts. So they're differentiating one x from the next and one y from the next. So they're not numbers in the calculation. Again, they're just subscripts, so they're like the naming system. So if we want to find the distance between these 2 points here, then I'm going to take the square root of the difference between the x's. So let's just say that you subtract the x's and then you square them, or square that difference. And then you will subtract the y's and square that difference as well. You would ultimately sum those two and then take the square root. So again, it's kind of a process of you're squaring to make the difference between them positive, and then you're adding them together and square rooting. Okay, so this is for distance between 2 points on the coordinate plane. So that would be in this context here that we would use the distance formula. If we have a straight line distance, so just like on a number line here, it's just one variable, like just in the x direction, just in the y direction, then it's enough to simply count the number of units or subtract the outright difference between the two. So that formula is a little more straightforward, a little more intuitive than in the coordinate plane. So for example, if I want to use this number line, so this is a straight line distance, to find the distance of each segment. So xy, that's between x and y here. Okay, again, the distance is the number of units between those two. So I don't have to use the full on distance formula, but rather just either I could subtract them, like 7 minus -1, or I can just count over 1, 2, 3, 4, 5, 6, 7, 8. That's 8 units. Alternatively, if you want to actually subtract the location, notice that 7 minus -1 is also 8. So you could calculate it that way as well. Next, if we're looking at WZ, the distance between W and Z, so between here and here. So again, it's a straight line distance, 1, 2, 3, 4, 5, 6, 7, 8, 9, that being 9 units. Or I could subtract the location, so 4 minus -5 is also 9 units. Okay. And then lastly, YW. So Y and W, those are the 2 endpoints. Okay. Notice that it's kind of directing us in the opposite from right to left instead of left to right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units. Okay. An important point to make is that distance is always positive. Always, always positive. It's kind of like the discussion on absolute value. So because distance is a measure of displacement, we want it to be always positive. So yeah, even if you're going from right to left, it's technically like you're going backward, but you still want to make sure you normalize it as a positive measure. And then notice if we had taken the 7 minus -5, like actually subtract their locations, we still get 12 as well. Okay, so that's a straight line distance. Again, it's just finding the in this case, horizontal displacement between 2 points. But in the case of this scenario, where I have now 2 ordered pairs, these would be in the coordinate plane. So I'm going to have to use my more advanced algorithm. So point P, which is at 1, 2, 3, 1, 2, 3, 4, 5, so somewhere over here. Q is at -1, 2, 3, and then 13, so it's like somewhere way up here. Okay. If I want to find the distance between these two, obviously I can't just sit here and like count because that's a diagonal distance. So this is where I have to use my distance formula, which to copy down, remember we said is the square root of x2 minus x1 squared plus y2 minus y1 squared. As far as designating your points, I always just like to go with the order in which they're presented to us. You can interchange them and you would get the same answer. Okay, so notice that they want us to first steal the x2. The x2 is -3. Okay, and then next we're going to steal the x1. That's a +3. Next we have the y2, which is 13. And then lastly, we have y1, which is 5. So this is just a good way to kind of visually see where you're going to deposit each of those numbers. So we're taking the distance, saying this is the square root of -3 minus 3, right? So I'm tucking in the green and the yellow number, plus 13 minus 5, okay? And again, before you apply that exponent, remember back to order of operations, we want to simplify inside of the parentheses first. So -3 minus 3, -6. 13 minus 5 is 8. Okay, and then before I can add those numbers, I do need to square them. So -6 squared, that's 36. 8 squared, 64. Add those bad boys together, it's 100. Square root of 100 is 10. So 10 units is the distance between those 2 points. So that's how that would look if we are using the distance formula instead of just a straight line distance calculation. Okay. Next one, we'll kind of drop the whole color coding. We'll just kind of illustrate how this works. But again, this is in the coordinate plane. So point A is at -1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, so somewhere down here. B is at 0, 15, so like way up here. And then we want the straight line distance. So once again, scenario where we can't count, simply count. So I'm going to have to use my distance formula. So square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, again, you can designate your points x1, y1, x2, y2. And just deposit those numbers accordingly. So we're going to take the square root of 0 minus -4. You want to be careful that you're on the lookout for when there might be a double negative. And then we're taking plus 15 minus -7. And so we end up with, notice that a double negative like this becomes addition. So this is actually 0 plus 4, so 4 squared, plus, this is also going to become addition, 15 plus 7 being 22. We want to square that. Remember that those guys cannot be combined until they are squared, just order of operations, so 16 and 484. If I add those two together, I get 500, so square root of 500. And that's not sounding like a perfect square. As a matter of fact, if I take the square root of 500, it's about 22.3. So I can say about 22.3 units. So we won't always get a perfect whole integer for that distance. Sometimes it's just an approximation. Okay, last one. So now we're looking for m, which is at 1, 0, and p, which is at 0, 1. And again, we want the straight line distance. So I can't simply count the number of units. So I'm again going to throw down my distance formula. x2 minus x1 squared. y2 minus y1 squared. Tucking in those numbers. Well, first let's designate x1 and y1. x2, y2. x2 being 0. x1 being 1. And then y2, 1, y1, 0. Okay. Simplifying inside those parentheses, we get -1 squared plus 1 squared. And -1 squared is just 1. 1 squared is also just 1. So I have square root of 2. So sometimes you leave it like that. If you wanted to get an approximation, it's about equal to 1.4 units. But sometimes we do just leave it as a radical as well. Cool. All right, now we are finding the distance of the following segments. So they're not actually giving you the points this time. we have to kind of write them in there. So for AB, I'm picking this point and this point. So we want to zoom in and see where these are actually located. So with respect to the origin here, A is at, let's see, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3, 9. B is located with respect to the origin at 2, 1, 2, 2, negative 3. Okay, so for the distance between the straight line distance between these two, those are the ordered pairs that I'm going to be using. So for this guy here, again, throwing down my distance formula, being square root of x2 minus x1 squared, y2 minus y1 squared. Stealing our numbers. Again, it's literally up to you. If you want to call this one x1, y1, x2, y2, or you can flip it around. Still, will give you the same outcome. So if I go ahead and calculate these numbers, I'm taking the square root of 2 minus 3 squared plus negative 3 minus 9 squared. So we have negative 1 squared plus negative 12 squared. 9, 10, 12, yep. Negative 1 squared, that's just 1. 12 squared, 144. So this is the square root of 145, which we could leave in that form. Do you want to go over? Oh, that won't actually simplify. Square root of 145, that was about equal to 12.04 units. So just depending on how they're asking you to express your answer, you might leave it as a radical or you might simplify it. Cool. And then next we're looking for AC. I'm going to start whispering because someone's trying to come in. We have AC already labeled. Or point A is already labeled. Point C is at 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, and let's just erase this because that one's insignificant for AC. So we'll call this guy x2, y2. Straight line distance between these. And so for finding distance AC, we're again using square root x2 minus x1 squared plus y2 minus y1 squared. If I tuck my numbers in, we're looking at square root of 9 minus 3 plus 0 minus 9. So square root of 6 squared plus negative 9 squared. So this is the square root of 36 plus, remember that anything squared, even if it's negative to begin with, will be positive. So this is plus 81. So 81 and 36 together making 117. So we could leave it as a radical or simplify it to give us about 10.8 units. So that's the straight line distance. Cool. Okay, now we have an application problem. So we're told that Paul and Susan are standing outside City Hall. Maybe we'll make City Hall the origin. Paul walks 3 blocks north. So 1, 2, 3. We lost track for 3 blocks north, 2 blocks west. So 1, 2. So here's Paul. And then Susan walks 5 blocks south from City Hall. 1, 2, 3, 4, 5. And 4 blocks east. 1, 2, 3, 4. Guys, after all these years, I still struggle with west and east. We want to find the straight line distance here, so let's label these points with respect to the origin. So Paul is at negative 2, 3. Susan's at 1, 2, 3, 4. 1, 2, 3, 4, negative 5. So we want to find the distance using square root x2 minus x1 squared plus y2 minus y1 squared. And so if we label our points here, again, it's up to you. in which order you label these, but x1, y1, oops, x2, y2. And if I deposit those numbers in, then we're taking 4 minus -2 squared plus -5 minus 3 squared. And if I simplify, this is the square root of 6 squared plus -8 squared. So we have the square root of 36 plus 64. Oh, these are looking promising because this is the square root of 100, which is 10 units. So again, notice that 10 units is not a conclusion that we could come to by just simply counting the points between the two. We do have to actually use distance formula. Okay. And then last one is just more open-ended. Create 2 coordinate points that have a distance of 5 units. What type of line was created? Really several different ways that we could go about doing this, but say we take one that's right here. And I'll pick another one here. I'm actually basing this off of a 3, 4, 5 triangle, knowing that if I want to find the distance like this, and then the legs, I don't know if you guys are familiar with this pattern, 3, 4, 5. So this is just a pattern that will always occur with right triangles. If you have one leg of 3 and the other leg of 4, then the hypotenuse would be 5. And then it's asking what type of line was created. Well, let's do a different scenario as well. Let's also create like a vertical and a horizontal case. We could also have one where maybe right here, 1, 2, 3, 4, 5. So here it's 1, 2, 3, 4, 5, distance of 5. That's a vertical line. Horizontal, maybe we're right here, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Horizontal line. This one would be a case, I guess we could just say it's a slant line. Slope, using the slope formula. Let's use this one for slope because this is just a nice review. So to find slope, do you guys remember that this is designated as m, and we take y2 minus y1 divided by x2 minus x1. Hopefully that rings a bell from algebra. You do need to designate your points in order for that slope calculation to work. So this guy over here is at 1, 2, 3, 4, -1. And then 1, 2, 3. This is at 1, 3. So for my slope calculation, we can take, again, let's label these x1, y1, x2, y2. So we'll have -1 minus 3 divided by 4 minus 1. So we have -4 over 3. So again, this one's very open-ended because there's several different ways that you could go about it. Just as you know as well, slope of a vertical line, this is undefined. Just a little review. And then the slope of a horizontal line is 0. Cool. I think that was it. Thanks for watching, guys.